I see a fluorine coming straight down. Here's carbon 1. Chlorine's going behind the board, so it's to my left. Also going a little bit up. What's here coming towards you and also a little bit up like this? H. So if it's coming toward you guys and I'm over here, coming to my right. Okay, let's look past carbon 2, something going straight up in the board. It's the alkyl group. Well, then the other two are H's here. It really doesn't matter. I mean, one's here and one's here. If we drew the H's in, one would be forward to my right, and one would be behind the board to my left. They're like this. How do I know to draw them here? Why didn't I draw an ellipse with the F? Because if the F was straight up, they have to be because it's sort of on the board. It's what is that? That's a third of 360. That's 100. Here, 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 that's 360. That's a third of 360? Sounds like 120. Okay, that is 120 because 90, that's a dihedral angle of 120 because 90 would be like this, right? That's 90. Yeah, that makes sense. That looks like 120. Looks like the bond angle is 120 between there, but see, that's not really correct. The bond angle in actuality between this and this is 195. Okay? All right, is that the best conformation? What do we have? Biggest groups on the front would be chlorine. With the halogens, the larger the halogen, the more steric preference. Sterics is its crowding demand. Now that can vary, but for us, as you get bigger, more sterically demanding. And then with the alkyls, I mean, bigger the alkyl, more demanding. A tert-butyl is more demanding than an ethyl, and an ethyl is more demanding than a methyl, that type of thing. So on the back carbon, the ethyl is the biggest, bigger than the H's. Right now, those two groups are gauche. We want to rotate these and make them anti. I'm just going to rotate the front, and I will get, I'm rotating the front, so the chlorine comes down, the F comes here. This is just like turning it like a wheel. H is here. Didn't do anything to the back. And there it is in the lowest energy conformation. The ethyl and the chlorine are anti. Question?
I know a lot of times you ask, at least in the last video, like how many energy conformations are there? You know, like how many different levels is there, I guess? Is there an easy way to do that?
It can get complicated.
Easier than drawing as well?
It can get complicated when you got multiples. If they were both chlorines, it would be a little bit easier because they would kind of repeat. It can be difficult, other than just drawing each one. Okay. Which one would you like to do over here? Somebody have one we want to show?
The third one.
Last one? Looking down the 4-3 bond. 4-3. We name this, what's the one position? This is 1, 2, 3, 4. You'd have dimethyl, 2 methyls at the 2. You'd have 2 things at the 2 position. Or if you came this way, you'd only have 1 thing at the 2 position. So this is the correct numbering. So looking down 4-3. 4,3, so we're standing here, looking down this way. This one will give us a different. Okay. I see carbon 4 here. I see something, I'm in the plane of the board. This is the board. I see something going straight up in the board. What is that? It's a methyl group. Okay? Now, a lot of times in my methyls, I like to put a ME on the end to clarify that that's just a methyl. Otherwise, it looks just like a straight line. I'm like, okay, methyl.
Is that acceptable, right? Any, is
Yes, I do that. Again, if we just draw the line, it's a little bit sort of, if it was an ethyl, it's just kind of more clear. So I usually put MEs on the end. Okay, carbon 4. Something's coming towards you guys, iodine. And if I'm over here, that's going to my left. I'm drawing what I see. I see this, but it's also going down a bit. There's the iodine. What's going the other way? H. I'm drawing H. Of course, in the Newman conformation, we draw in the H's. Okay, let's look past there to carbon number 3. I see, here's the board. I see something going straight down in the board. Here's the ground. I'm standing on the ground. Going towards the ground, straight down the board is the T-butyl group. That's a tert-butyl. Tert-butyl. Carbon 3, there's something going towards you guys. Methyl. So it's going to my left. And a little up. To my left, and a little up. What's on carbon 3 going behind the board? To my right, if I'm standing over here, behind the board is to my right. There it is as drawn. Is that the lowest energy conformation? Front carbon, the biggest group, I'm going to say iodine, and huge halogen. Back, tert-butyl. Right now they're gauche. I'm going to rotate the front carbon. Either one, you can rotate the back, it doesn't matter. Make the iodine up, make the H here, and make the methyl here. The back I didn't do anything to, so the methyl, H, tert-butyl.
But the methyl was on the other side of the iodine. Oh.
If I turn the iodine up, it's just like turning the clock dial. Iodine comes here, methyl comes here, H swings over here. Just rotate that. Here the H is up over here. I can just rotate it. If that goes up, the H swings over. See this front, you can just rotate. Now on the board it looks like it's planar, but in reality they're all three sort of coming towards you a little bit. There we go. Now we have the tert-butyl and the iodide anti. For us, that's the best. What's the relationship of the methyls in the lowest energy conformation? They're anti as well. Yes. The two hydrogens are anti. Okay. Let's see what else. Can a Gauss conformation sometimes be preferred? That is, are there exceptions to having big group anti? Yeah, this compound right here, the OH is actually preferred to be Gauss. Now remember, we draw it like this on the board. There it is on the board. So what are we talking about? We're talking about, well, how does this thing rotate? can we draw it in a different way to show this? And we're like, okay, these are kind of big groups. They're oxygens, OHs. Oxygen's bigger than an H, so these are going to want to be maybe anti. By the way, that's sort of why when you draw things on the board like this, you do sort of a zigzag, because this is naturally anti. Okay. But is that preferred? Can you show it in this representation? Well, actually, no. Actually, the two groups are preferred to be gauche. Now, this is drawn like this, the front carbon straight up. The back OH is not preferred to be straight down, anti. It actually prefers to be not eclipsed, but gauche. That's actually more the preferred. And that's why. I mean, and that's showing it in the Newman. Why does gauche preferred?
Hydrogen bonding? Yeah. Okay.
Yes. An intramolecular hydrogen bond. If they're anti, these can't hydrogen bond, they're too far apart. So these things are, they're hanging out, having a Memorial Day drink, or
Yeah, not this one.
and what are they doing? Do they more like this, or do they prefer to come up in here and be more like that? Well, yeah, because when they come up in here, that H and these electrons can start interacting, and it holds it up more like that. Now there's energy here, but it holds it like that. Hydrogen bonding is why the exception here, and these prefer to be gauche. And this is known in maybe from molecular modeling, where you teach the computer how to be real smart. That's an exception. Hydrogen bonding down here. Hydrogen bonding, intramolecular hydrogen bonding is often seen. You don't always have to show it in a Newman. Can you envision some intramolecular hydrogen bonding down here? Can you show it without doing a Newman? Yeah. You got this H bond, a donor here. What could be an acceptor? Here. So you can illustrate this by maybe redrawing the compound. Maybe rotate this and make the H up like this. Sort of something like this. That's basically where, instead of the H being down like this is tetrahedral, right? There's an undrawn H here, so the OH. I just said, hey, it rotated up because now it can do hydrogen bonding. And you can just rotate it like this. So I didn't have to go to a Newman, but I can be aware and show that here. And also when you hydrogen bond internally, you think about the size ring that's sort of formed. 1, 2, 3, 4, 5, 6. A 6-membered ring. Okay. By the way, what are your best size rings?
6, 12.
We didn't, I don't think we mentioned it over on the heats of formation table. Are 3 and 4 good size rings?
No.
No, they have ring strength. What about 7, 8, 9 size rings? We didn't mention those. Are those good?
They stretch.
They actually become the bond angles want to stretch too much. A 3-membered ring is like a 60-degree internuclear angle, interatomic angle. The bigger the ring, they go beyond 109.5 and it has to stretch out. 5 and 6 are your best size rings. And so this, you might wonder, hey, is this going to want to reach around here and do hydrogen bonding? Yeah, a nice 6-membered ring. On the other hand, if this hydrogen bond donor was way down here, and for it to reach around, you form like a 12-membered ring, it's not going to be quite as good. It's kind of like if I was going to clap hands, this is good. But if my arm was twice as long, I'd be doing this. You know? Not so good. So you get the right. Okay, let's see where we're at. Let's take a short 2-minute break and then see what we need to look at to finish things up. Last question.
For the two,
Yeah.
came down at the two, zone,
A little louder.
For the Newman confirmation question, that's when I'm looking at the 2 to 3 bond with the Brundle on it. Is that asking, like, if you were to draw the initial Newman, structure, would it be like a cliff? Is it a 2?
It might be, and I think it probably is.
Okay.
We might do that real quick. 2 minutes.
I'm so confused about that one. I'm like, this definitely looks eclipsed. So I actually asked, this one, if you draw the Newman, it comes out, it's eclipsed. It just seems counterintuitive to what we've been doing.
We'll look back at the physical properties handout with this acid-base extraction. We'll look at page 37 in the workbook. Page 37. One of them is drawn in the chair. Okay, guys, somebody mentioned this one here real quick. Let's look at it. Looking at the 2-3 bond, this would be 2-3. Carbon 2, I see a methyl coming straight down. I see a bromine going towards you guys, so it's on my right. And there's also an H there coming this way. Carbon 3, I see an ethyl coming also straight down. Correct?
Yes.
So yes, that ethyl group is eclipsing the methyl. Now it's directly behind it, but I can't draw it directly behind it. So you draw the eclipsing a little bit to the side, okay? Now I see a methyl going up and back, so up and to my left. Well, it's eclipsing that H. Here's one thing to keep in mind. I drew this here a little bit to the right of the methyl, like on a clock dial. So I'm going to draw the methyl a little bit counterclockwise to the H. Whoops. What else is on carbon 3? There's an H coming forward, correct? Right? We don't draw it in, but there's an H coming forward. So it's to the right, a little bit up. It's actually eclipsing the bromine. I'm going to draw it a little bit counterclockwise to the bromine, something like that. But yes, the original, as drawn, things are eclipsing. Is that the best? Well, no. Eclipsing is never better. Biggest group on the front, methyl bromine. I'm going to say bromine. Biggest group on the back, ethyl. I want to make sure that these are antis. I'm going to rotate the front, the bromine here. I don't have to rotate it much, do I? I just want to rotate it up here. I'm rotating the front, bromine now straight up. That puts the H here, the methyl here. We did not rotate the back, so the ethyl's there. The H is here. And what else is on the back? The methyl. We got two methyls, one on the front and one on the back. Now the bromine and the ethyl are anti. Yes, the original is sort of in a eclipse. Bromine, ethyl, anti. Question. When the bromine and the hydrogen are anti, what's the relationship between the methyls?
Gauche.
If the bromine and the H are anti, what's the relationship between the methyls? Some people say gauche, I say gouache. It'd be gouache. The bromine and the H are anti. Let's draw that like that. I'm not saying it's the best. I'm going to keep the back the same. H, methyl, ethyl. The bromine here, because I said if the bromine and the H are anti, if the bromine's there, we got what, H here and methyl here? The bromine and the H are anti, the methyls are gouache, yes. Variety of questions if you just know your terminology and how to rotate things. Okay, let's look over here. We skipped this in the physical properties. I should really move this to the acid-base handout because it's really acid-base. Commonly to do extractions using your separatory funnel, which is in your drawer. Tends to be your most expensive piece of glassware. To do separations, we can separate these two compounds through an acid-base extraction using an organic solvent and some type of aqueous. Here we're using aqueous base. Dichloromethane, halogenated, more dense than water, lower layer. The aqueous will be the upper layer. But the aqueous has base. Will base react with either one of these?
Yes.
Which one's acidic?
The carboxylic.
Carboxylic acid. This is condensed with carboxylic acid. Here's sort of the question where we could have some vagueness. Is the alcohol acidic enough to be deprotonated by hydroxide? What's the pKa of an alcohol?
16.
That's about 4 to 5. This is about 16. Well, let's judge. If this reacted with hydroxide, we're looking to do what? This is a base. We're looking to deprotonate, remove the H, so this would give what? O minus plus what? Plus water. pKa of 16. What's his pKa? Also 16. Your equilibrium is no good. It ain't going to work. Only the carboxylic acid will be deprotonated. This ain't going to work in practice. So we mix these up. The reaction takes place. This becomes the anion. And the anion is going to prefer the water layer. This guy does not become an ion or anion. It's going to remain neutral and prefer the dichloromethane. But now you can just manually separate the layers by draining one layer into one flask and one layer into another. You've separated the two. Now this is in the dichloromethane. The dichloromethane can just be evaporated like on a rotary evaporator. Evaporate the solvent, leaving behind the non-volatile compound. You've separated it. The carboxylic acid is in the ion form. Now you can get rid of the water, but in practice you don't want to do this. You're also going to have excess sodium hydroxide. Does it show it here? No. Instead, what we can do is we can acidify, neutralize, take it to the other side. What's your favorite acid that you want to neutralize with?
HCl.
This is basic. Okay, we used base. Like in the solubility lab, we used base. Yes, in lab we use sulfuric acid. You can use HCl. That's going to put protons on everything. Is this strong enough to accept the proton? Well, is it a good base? Is it an anion? Yeah, it's an anion. It's going to take the proton back. And when it takes the proton back, what do you get? Well, you get back your compound that now with the proton back on. If this is not soluble in water, what may happen once you put the proton back on? It may what? May precipitate. If it's not soluble in water and if it's a solid. And then if it precipitates, then you can maybe filter it off or something. That's how you would do an acid-base extraction. We sort of talked about that earlier on today a little bit. Okay, things are described down there. Any questions there? Standard extraction process, acid-base. Ultimately, you can get something to become an ion. It's going to want to go into the water, where non-ions are going to prefer organic. All right, where are we at? That's it. That's material. How are we doing with IR?
I have a quick question. At the top of that page, there was 2 exceptions for organic salts that are highly polar. Are we going to have to do anything with that, or is that just kind of like an FYI?
It's an application, exception, FYI.
Okay.
I mean, kidney stones. Why do kidney stones? They precipitate in the kidney. Well, you lots of water around. But the kidney stone is actually that ions. Why do the ions precipitate in water? Doesn't sound right. Because of an exception. Calcium oxalate is actually, even though it's ionic, it's not that soluble in water. Kidney stones and gout, there's a couple of, unfortunately, common medical things. Yeah, I think the application is more important stuff, really. And what hopefully is the more interesting stuff. And why are we learning this stuff? But yeah, it looks ionic, you would say, but you said it's soluble in water. Well, but there are some exceptions. Just like sugar is a neutral organic molecule. It will dissolve in water. Not easily, but it will. That's because it's got a lot of OHs, does a lot of hydrogen bonding. Takes a little warming of the water usually. Okay. Let's see how we're doing on page 37, IR. You may have done these already. I'll go through the way I would do it. Okay, assign compounds to IR. Magic line of 3000, yeah? That's a straight line. That's a straight line. What is this? sp3CH. Does it seem to have any sp2CH?
No.
You know, if you got a little ruler, you can, something about the magic line. Have I ever seen sp3CH above 3000? Yeah. There's always an exception, but it's a pretty damn good rule, 3000. It looks like there's no what? Like there's no sp2CH and stuff here. What else do we see? What is this, 1500? That's fingerprint. How about a carbonyl? Do you see a carbonyl? 1700? That ain't a carbonyl. Carbonyl is usually a strong, intense peak. You often get peaks, sometimes they're just sort of rogue peaks. What is this?
Could be an NH.
Why do you say it could be an NH and not a...
Because OHs or OH, that's where she weak to be an OH.
Yeah, OHs tend to be definitely stronger. NHs sometimes can be weak like that.
And there's no just purely CH compound up there. So the only thing it could be an NH. It's above an sp3CH.
Right, testing. Your answers are up there. I would start looking up above. Like you said, there's no just plain, this looks like just hydrocarbon, no carbonyl, no triple bond, but there's not just a hydrocarbon answer up there. So which one is it? Well, let's knock them off. Is it any of them on the first row? Why not?
Because there's no COs. There's no C double bond.
Because all the ones on the first row contain sp2CH. Right? Every ring has an sp2CH. That would give peaks just above 3000. So it's none of those. Also, aromatic, all those are aromatic. What else would an aromatic give in the IR?
The mountain number.
It's through here, sort of the aromatic signature. It's pretty plain, simple through there. There's not much going on. It doesn't look like an aromatic. So I don't think it's any on the top row. Okay, is it G?
No.
Well, again, the OH typically is much stronger than this guy would be. I don't think that's it. Is it I?
No.
No carbonyl. Is it J?
No.
No carbonyl. We also don't have a boron OH for the carboxylic acid. It looks like it's H. If it's H, does that fit? Lots of sp3CH. Carbon-carbon is fingerprint. NH. We have to say that this must be an NH here, and it's H. NHs can be weak, particularly if they're non-conjugated. Is this lone pair conjugated?
No.
No. If the nitrogen was conjugated, it typically makes the NH strong. It's pretty darn weak. But again, you can't say it's nothing, then there would be no answer up there that fits at all. Next one. Oh, something strong here. Magic line.
That's an OH. Yeah.
1500. It looks like I have both sp3 and sp2ch. This looks like a OH. Now it kind of is broad, I mean, I don't know. What does this look like? It's like an aromatic, and you also have sort of aromatic CC. Does this compound have a carbonyl? C double bond O. It'd be about 1700 or so. No carbonyl. It looks like maybe an aromatic with sp2ch and an OH. Do we have such a choice? Well, if it's aromatic, it's only top. What's the answer here? C is in Charlie? It's an aromatic with an OH. Not only is there, it also has the sp3ch. You got that one carbon that has sp3chs there. The rest are sp2 and then the OH. C, Charlie. um, 3000. Is this yes or no? It definitely has sp2ch. I don't know. It looks like it does, but it also looks like it's trying to not have sp3ch. We'll see. This funny looking stuff. A strong peak here at 15, 16, pushing 1700. 1686, is that what that says? Maybe that's 1686. Looks like what? Looks like carbonyl. Carbonyl with definitely sp2ch. Let's see what type of choices we have.
There's definitely a ring structure in
Aromatic, is that an E? Yeah, we got some here. You got sort of here. It looks like it might be an aromatic. It's definitely got sp2ch, and the only ones that have sp2ch are the aromatic ones because there's no alkenes.
I thought B.
It's got a carbonyl, so A, E, or F. This doesn't have a carbonyl.
I put B.
This has a cyano group. Where does that give a signal? It's carbon triple bond in. CC triple bond and CN triple bond are both about 2200. There was nothing there. We can get rid of that one. A or E?
B also has a possibility.
You're right, B.
That's the one I put on. Oh. Is that an H bond?
You think that's an NH?
Yeah, it's small again, so it can't be an OH.
Yeah, something I know that I mentioned earlier. This lone pair is conjugated. That NH is going to be strong.
Okay.
But here's the thing. I don't know if I covered it in the video. Carbonyl placement. Carbonyl placement. I may not have covered this in the video. The carbonyl's at 1686. Amide carbonyls typically, I want you to do this, I want you to look in your table. Where does it say for amide? Can you get a difference in carbonyl position? Can that help you? Table in the handout.
Yeah.
1680 to 1630. Okay. I wish I didn't go as high as 1680, but I would say more like 1630 to 1660. So that's not a definitive answer for you. Amids typically have lower carbonyls, more like mid 1600s, or even lower. 1640, 1650. Also, we sort of saw one with a weak NH. It's, you call that maybe weak. What do you think this is here? Anybody got something for that guy? Because it could be something else other than an NH. Carbonyls are very prone to giving what? Overtones. How do you tell if it's an overtone?
It's a little less than double.
Double minus a touch. Double would be what? It would be 3400 minus 28. 3372. 3372. Is that double? Yes, double. Okay. Minus a touch. Where is this peak at here? One, two, 3. It's between 3300 and 3400. I can't read that. Is that 3352?
Yeah.
I think it's 3352. Double minus a touch. Usually not quite. I wish it was more like 3362. It's usually, but I think it could be an overtone. It's also a little sharp. It could be an overtone. So ultimately, this, not for the amide. It could be a little water if this is an actual spectrum. Carbonyl placement, I don't think I covered that in the video. Amides typically have low carbonyls. Otherwise, that's it. Last one.
What's the answer?
I think the answer is this guy here. E, as in elephant. Carbonyl. Thus, it does have sp3ch. Thus, this must be sp3ca a little bit here. Not much. I thought it was a little bit. One at the bottom. Got a nice big peak at 15, what is that, 1700? Is that, what is that, 08? Is that right, 1708? What is that? Nice carbonyl. We got a peak here in the 2200 region. That's either CC or CN, triple bond land. What's the exact position of this peak? 20, is it 2230? Okay, 2230 to me means it's the C triple bond N, because usually the C triple bond C tends to be below 2200, like 21 something. That's a fine detail you may not. Also, is there even a triple bond, carbon-carbon triple bond up there? Alkyne? So I know it can't be it. It has to be a C, right?
There's only one of them with C and C double bond O.
Ah, so you think you already got it. The old test-taking strategy. So we don't have to look any further, is that right?
F. F is the only one with both.
F. Ah, I thought I recognized that aldehyde. F is in Frank. What is this here? Because look, it's only a wee bit, but usually your stuff just below 3000 is like right on the edge. This is a little bit further to the right. then right against the line. What are those peaks for?
Oh, those are the SP2,
What functional group is in the, what two functional groups are in this F, Frank? Nitrile or cyano group, and what's the other one? The carbonyl containing functional group. You can call me out, right?
the aldehyde SP2CH.
Look in your table. Where does it tell you about an aldehyde? For the carbonyl.
2830 to 2700.
Where does it say? If you look under the CH, Appendix E, the page that says Appendix E, right? Look under the CH, the last entry is for an aldehyde, the RCHO, that's aldehyde. The H of an aldehyde, where at?
SP2.
The H of an aldehyde is actually sp2CH. But that one is not above 3,000. That one is actually below 3,000 at about 2750 and 2850. Usually two peaks, 2750, 2850. Those are your two peaks for the aldehyde CH. Why is it two peaks? Well, it could be a strip. It's probably a three-bond thing involving the CH, but you've got maybe a symmetric and an asymmetric. That's giving both frequencies. This is your aldehyde CH.
So is the aldehyde not supposed to be down there with the 17, 15, and 17, 30?
But that's the carbonyl of the aldehyde. We're talking about the CH of the aldehyde.
So the functional groups, each individual piece of the functional group sits in a different area of the IR graph. So like if you have an aldehyde, it's always going to have these distinct pieces.
Yes.
A big CO and a small sp2.
Yes. That's what we're doing.
Yeah, I'm trying to recognize.
Peaks represent functional groups, yeah. But individual bonding of the functional group.
Yes.
So there's a little IR. How we doing? Last question. Cover everything? Test. Want to have test tomorrow, or you want to move it to next day, Thursday?
That would be
Thursday.
Thursday.
I'm down. Thursday.
Any objections to moving it to Thursday?
No.
Tomorrow we would start new material for test 2.
That's okay.
Any objections?
Nope.
Tomorrow we start new material for test 2. Test will be on Thursday. Lab. Tomorrow. Tomorrow, today is Tuesday. Lab on Wednesday and Thursday. We're doing determination of 2 unknowns. Each of you will be given a liquid unknown and a solid. The liquid will first have to be distilled. Video covering distillation is on the YouTube page. Please have watched the video. Pre-lab, etc. Any questions about lab this week? When you come to lab tomorrow or Thursday, your solubility lab is due. The SciFinder worksheet to make up for the missed lab today and yesterday. Any questions about that? That's due on Friday. Question?
Yes, right.
I'll provide handouts tomorrow in class for that. We'll begin alkenes. Alkenes. Before class? You want to do that again? 8:30? I'll be here at 8:30. Nomenclature was by video only. What am I forgetting to say? Test format. We can mention tomorrow. Test format similar to, I'll go ahead and do it now while we got a couple minutes. We have similar format to quizzes and questions in the workbook. Most of those are kind of short answer. There do tend to be some multiple choice, okay? Mainly because standardized exams which come around, for me at the end of Organic 2, it's all multiple choice. So I want to kind of remain in the habit of some multiple choice. But largely short answer like quizzes and stuff. What have we covered? Typically start with nomenclature, okay? Typically first page tends to be multiple choice with me. Second page starting short answer. This could vary for test. Short answer, what do we do? Hybridization, structure, little structures, charges, bond strings, that type of thing. Acid-base chemistry, yeah. Conformations. Looks like that's the end of class. We'll see. We'll talk more tomorrow. Lab report this week in lab, yeah.